Hi guys. So, new quarter, new unit. This unit is all to do with rotational motion, and then we end with gravity. Okay, so our first learning target here. Students will describe rotational motion using mathematic and computational thinking. This includes the role of torque. Students will describe factors determining stability of an object and the apparent forces in rotational reference frames. Okay, so we're going to talk about rotational motion. A big component of that is going to be torque. And then we're also going to kind of recognize and talk through what constitutes something to be stable. Like if it's tilting, how can we find that stability? Okay, so first we need to go over a few different definitions. And the first is linear speed. And linear speed is mostly what we've been dealing with so far. It is distance traveled per time unit, right? Like meters per second, okay? So if we now take this linear speed and we want to attach it to circular motion, it's going to be that distance traveled per time. Now, something interesting to note here, maybe kind of small, but let's say that this is a merry-go-round or some kind of like a CD or something like that, okay? And what's going on here is, let's say that we have a person or an ant, or however we want to look at this, right on the very edge here, and it's going around in a circle, okay? So let's say that it takes 1 second for this person to go from here to there, right? Now, look at the distance that was covered there, and in the unit of time being 1 second. Now, what if there was another person on the merry-go-round and they were inside? Okay, so we have someone on the outside and then someone on the inside. So look at how much further the person on the outside travels versus the person on the inside. That's a lot shorter distance. And so the linear speed is greater for the outer edge of a rotating object versus the inner edge of a rotating object. The rotating object that we're probably all familiar with is like a ceiling fan. So next time you're laying on your bed looking up at your ceiling fan, what I want you to do is realize and look at how the outside of the fan actually has greater linear speed versus the inside of the fan. And that it's easier for your eyes to actually track the inside of the fan versus the outside of the fan, and that's the reason why. Now, let's see, the speed of something moving along a circular path can be called a tangential speed. So this linear speed or tangential speed, we use those terms interchangeably. And a good way of thinking about this is you could say, well, what's the instantaneous velocity right at this moment? Okay, like we're spinning around, but when we hit pause, right? We pause time and we go, right in this moment, what would be that velocity vector of that person? And it wouldn't be a curved vector. It would be a straight line that was tangential to the circular motion. Okay? And that's why. And so like as this continues on and now the person's all the way on the other side, their linear velocity for that moment would be right there. And we've seen this before, we've talked about this. It's friction, or it's like holding on to something, that kind of force that keeps you going in the circle, and so it's constantly changing that linear velocity, the vector, but the linear speed could be remaining the same. Okay. Rotational speed. Now, rotational speed is different. Rotational speed is the number of rotation per unit of time. Okay? So we said that in 1 second, this person is going this far, right? And so it takes 2 seconds for there to be a full rotation. So one rotation occurred in 2 seconds. And so that would be half a rotation per second, right? Half a rotation per second. And that would be a rotational speed. Now, what about this one that was on the inside? We know that it has lower linear speed, but what about rotational speed? This inside person still covers that same distance. They still rotate half a rotation per second. And so the rotational speeds for both people are the same, but the linear or tangential speeds are different. All right, we have a couple of symbols that we see a lot, so I want to take a moment to talk through those. Theta is our angular displacement. Omega is our angular velocity. Alpha is our angular acceleration. And then the Greek letter tau is our torque. Now, we see something really interesting here. We've been dealing a lot with linear motion, and this is circular motion, but there's amazing correlations between the two. And so, like, linear velocity is a change in position over a change in time. But angular velocity, right, we just learned about that, angular velocity is omega, is a change in angular displacement over time. Okay. Let's draw that. Okay, so again, we have this circle going in like a merry-go-round or whatever. Here's the very center point of our rotation. And you could treat this like a unit circle. And that if we go from here to there, that this would be theta, right? That would be our angular displacement, the amount of displacement based on the change in angle, okay? Okay, now let's keep going. We know that acceleration is a change in velocity over time, and then angular acceleration, okay, is a change in angular velocity, that omega, over time. And then we have a couple of kinematic equations here. We use those quite a bit when we're doing linear motion. And so we know that like a final position would be velocity initial multiplied by 1/2 acceleration times squared. And it turns out that our theta, our angular displacement, is an angular velocity initial plus 1/2 times by alpha, which is our angular acceleration multiplied by time squared. And so there's just these amazing correlations between the two. Okay, where are we at time-wise? Okay. So now that we've talked through like what is rotational motion and how we can define that, a big part of rotational motion is torque. And one part of understanding torque is realizing that torque is not a force. It has a force component to it, but torque itself is not force. Okay? And so let me give you an example of this, and we'll come back to it a couple of times. I have my pen here, and I'm going to hold onto this pen, and I'm going to try to do everything I can to resist motion of this pen. Okay, and so I can apply a force. So on this side, I'm going to push on the pen. Okay, and I'm pushing quite hard, but the pen is not moving, and that's because we are resisting that force, right? But what if I just change the direction of that force? Instead of pushing perpendicular, why don't I push, instead of pushing parallel, instead of the force being parallel, why don't I push it perpendicular to the object? And when I do that, it all of a sudden becomes really easy to move. It's easy for that rotation to occur. Even though I'm pushing really hard here, there's no rotation occurring because there's no component of the force that would cause that rotation to occur. But as soon as I give any component of that force a perpendicular component there, then rotation will occur. And even if I try to resist that, it's a lot harder to do. Okay, so that's what torque is. Torque is the perpendicular component of the force, but there's another side of this, and that is not only how hard am I pushing, and not only the angle of where I'm pushing, but where I'm pushing in relation to that rotational motion. And so in a little bit, we're going to talk about how if I push here, I have more torque than if I push there. That like I can push with a little bit of force here and it starts moving, but I have to push with a lot harder force to get it moving when I'm closer to that lever, to that rotational point. Okay, so that's torque. So torque is produced by the turning force and tends to produce rotational acceleration. Okay? Torque is different from a force. If you want to move an object, you can apply a force. If you want to make an object rotate, then you apply a torque. Okay? Lever arm. So back to the pen, our lever arm here, or our moment arm, again, two terms used interchangeably, from the point of rotation. Okay, so like if this is where it's rotating around, from the point of rotation where I am applying the force, that distance, that's the lever arm. Okay, so if I'm going to push on the very, very end of it, then that's the lever arm. Or if I'm going to push here, then that's the lever arm. Okay. Okay. Okay, so what we're going to do when we come back to the next video is we're going to make some predictions about torque. Okay? And we're going to kind of define this equation that we're going to be using, and then we'll jump into our example problems.